Good. So I'm going to talk about finding similar GitHub repositories, but it's going to be, a bit at scale, like hands-on production experience. You can scan this QR code to view it on your mobile device. We have Wi-Fi here, so probably for some of you, it's more convenient. And while some of you are doing that, let me just introduce the objective of this talk. So finding similar GitHub repositories is a bit, a subjective thing. So for some people, similarity means one thing. For other people, it means different thing. And it pretty much depends on how do you define the similarity. And it turns out that you can have multiple ways of defining what the similarity is. And so let's talk about it. If you talk about similar items, it's usually in the context of getting recommendations, right? Because usually if you have something similar, you can offer your customers, clients, these similar items as a recommendation. And using this experience from recommendation engines, usually have two ways of doing that. It's collaborative filtering and content analysis. It's not that fun with collaborative filtering because it has nothing to do with the source code, actually. So it's just repositories, people who contribute to repositories. You have this contribution graph. Anyway, we have experience in this field. Igor is going to give a lightning about it after lunch. And I'm sticking with the second way. Oops. This is our plan, how we're going to find similar repositories. It's very simple, just two steps. The first is you need to find a way to turn every GitHub repository into features. And these features are going to be just a fixed dimensionality vector, like 300 dimensions or so. And after you do that, you just find nearest neighbors and get your similar repositories. We need to define what is the source code and how can we use it to extract features from repositories, because repositories are source code usually, right? Of course, on GitHub. If you try to just do source code highlighting, you will find different tokens meaning different things. You will have keywords, this orange stuff, which define the program structure. You will see identifiers, which encode some semantics and probably some natural language inside the source code. You will have literals, constants, string literals, and in contrast to natural language, this structure is only one. You cannot kind of define different trees for the same sentence. And besides, since your repositories are on GitHub, you have Git, you have version control system, and you have history. You know how each project was developed through time. You have dynamics, and usually it's not a single person who writes the source code, so you have different people working on it. So it's just an example of git blame on a source code file. You see date stamps, you see people, and this is very valuable information which you can use to actually define similar GitHub repositories. To summarize, well, we call it source code machine learning and source. Probably it's a bit vague. Probably we should name it source code analysis, but this is our working drafts. In our vision, source code machine learning is on the intersection of three different domains. The first is natural language processing. The second is just algorithms dealing with structure, compilers, this traditional stuff. And the third is more, humanitarian style. It's history, it's all social features, it's contributions, it's how people interact. And yeah, if you take all of this into the same spot, you will get source code machine learning. If you focus on the content, there are multiple kind of sweet spots at which you can address your machine learning attempts. You know, you need to define some input data and work on this input data, and you have multiple sources of this input data. You have development history, this version control statistics, as I said. You have project structure, so basically file system, how project is organized, how files are stored on a file system, dependencies between modules. You have language distribution. So yeah, I will talk about each one later in more detail. So just let me name the rest. README files. It's not only README files, but all the text information. It can be HTML, and can be some documentation. It's just a bunch of natural language documents which you can use. If you parse your source code into AST, you will have trees, and you can do fun stuff with trees. Finally, if you look into specific leaves of those trees, you can use comments and constants and literals and identifiers. Okay, so we can apply development history to find similar repositories in different ways. Just one example is that since all the technologies usually have this, this life cycle. Does it work? Okay, great. So, where should I post? So, at first, the technology just appears. It has early adopters. Then it's a peak. This can be very long. Then it starts to descend, and finally it dies. From our experience, this happens to the majority of GitHub repositories. There are some notable exclusions. For example, Linux kernel is still active since 20 or even 30 years, it appeared. But usually most of the projects, they follow the same curve. And depending on the domain this technology was created in, this interval can be between 1 and probably 10 years. If you take JavaScript framework, it can even be less than 1 year, who knows. If you just plot commit frequency through time, it should correlate with this technology lifecycle. So first you have just core developers, then the technology goes mainstream, the project receives a lot of attention and lots of PRs and contributions, and then it starts to, not be trendy, not so cool, people start contributing, and the project slowly dies. Especially can correlate with the age of main contributors. If they are like 20-something, they are most likely to accept your PRs, and if they are 40-something, usually it's less likely. But okay, I'm diverging. Well, project structure, as I said, pretty straightforward. So we just compare the way project is organized, and it works pretty well for finding, for example, websites, because usually your website is using some engine or framework, and this framework, it dictates you the structure of your project. I don't know, Django requires you to put your models into one folder, you use in the second folder, you place your templates in the third folder, and yeah, the same for PHP, the same for other languages, Ruby on Rails, and if you just compare the structures, you will find a lot of similar projects using the same technology. Speaking about language vectors, I call this alignment because it's very rare nowadays that a project is using just a single language. Usually it's at least 2 or 3. If you take just, for example, C library, It has a bunch of shell scripts to be built, or make files, or CMake configuration, or whatever. Probably some Python scripts to automate tests. So usually it's not a single language. This is why I call it a distribution. And if you click on your project top on GitHub, you will see this kind of line with different languages, with different proportions. And it turns out that alignment is a fixed ratio of every language in the distribution. And for similar projects, it tends to be constant. It tends to be the same, more or less. Works really good for example, C++, works really good for Python. It's not that, precise, but you can use it to cluster all the projects on GitHub, for example. It works really good. Well, README files is just a polygon for applying your NLP skills. You can do a lot of interesting things. Usually it's Markdown, and since it's Markdown, you can parse it, you can extract titles, you can extract source code snippets, you can do really funny things with it. So we have a data set, by the way, extracted from all the GitHub. It's about 16 million GitHub repositories. And as we see, only 2/3 have README files. Well, it's still a lot, so I think it's useful to play. Extracting ASTs from millions and millions of repositories is challenging because, first of all, you have about 400 supported languages, and writing 400 AST parsers is not that easy. We started our project, as I mentioned it earlier, it's called Babelfish. It's like a big umbrella of different subprojects. We call it drivers. So every language has a driver which extracts AST. And since we are not, compiling sources, it can be done very nice way. At scale, and it should work really good. I think we are going to, well, I think we have already released it in some way, but just didn't hype about it. If you extract ASTs from all the source code, it will allow you to generalize and find probably the same thing as Charles did in the second part of his presentation, where he found similar code patterns, frequent code patterns, right? You can do the same with trees to try to infer algorithms. We have a theory that it should be possible to extract, for example, all projects which have sorting, bubble sort or quick sort inside. Talking about comments and literals, it's not that Massive has README files. This is why I call them short distance NLP, ironically. Still, you can do funny things. For example, on the recent MSR conference, Mining Software Repositories in Buenos Aires, where we took part in, it was a really nice example of using comments to do sentiment analysis, because usually the style you put into your comments reflects your mood and reflects kind of what do you feel about the project. Especially for junior and younger people, they tend to swear a lot in a project which they don't understand much, or sometimes it reflects even your experience. So at project on MSR, it did sentiment analysis, not on a very big data set. The data set size was about how much, 10, 50 GitHub projects. Still, they had funny results. So it works, and it's very interesting to repeat this project at scale on millions of GitHub repositories. You can just put a metric for every project, how positive it is. So, project is too negative, I'm not going to contribute to it. Finally, identifiers. We have a data set which we already extracted, so you can use it. Everything is open. I will try to convince you that identifiers is a very rich source of information which you can use for machine learning. They carry not only, NLP information, but also some very algorithm-specific information, and they were available. Let's try to build our pipeline to extract all identifiers from GitHub repositories, turn them into features in some way, and use it for nearest neighbors. Since we don't have Babelfish yet, we cannot use abstract syntax trees, and the most pragmatic approach is to apply some parsing library. Pigments, highlight.js, any source code highlighter you know, it is usually regex-based. Regular expressions parse the files if they're written well, because in our experience, some regular expressions they tend to be infinite in some languages, so it sounds that easy. Yet still, we managed to apply pigments to all the source code after, of course, classification, because you need to classify every file to the language it belongs to. Usually, it's easy, just look at the file extension and that's it. But some languages have the same extension, and some files have a misleading extension. So, like in 5% of all the cases, it's not that evident, and you need to go deeper and even apply some basic machine learning to determine the language of the file. What's exciting about this is that it's perfectly parallelizable, and you can run it on Spark, and it works pretty well on Spark. Doesn't have any data dependencies, so yeah, it's good. I mentioned that we use pigments. This is how we do it. Pigments assign every token a type and a value, and we filter all the tokens which are of token.name type. It's identifiers. After that, we do splitting, because people give like craziest names to identifiers. Like some identifiers are super crazy, like 100 or even 200 chars in some Java enterprise-ish projects, and it's a good idea to do splitting. This is how we do splitting on the examples listed here. Actually, it's our test suite. It's camel case, it's underscore, it's how to say it, Hungarian notation, we drop numbers, and the algorithm is on GitHub gist, so you can view it if you want. After we do that, it appears that it's useful to apply stemming. If you draw the histogram of identifier size frequency, it turns out that 6 is the most probable one, and the thing is, you cannot stem all the identifiers, because if it's only 4 or 3 chars, stemming will give you a lot of collisions, and you don't want collisions. So just experimentally, empirically, it can be seen that 7, 8, 9, and so on and so forth is like a good balance between the number of collisions and profit which you get from stemming. After we get this, bag of words, because it's what it is, it's a bag of words with frequencies, you apply TF-IDF. Well, nothing exciting here. It's just taken directly from NLP, topic modeling, any model which works on bag of words. You get something like this. So, for example, for TensorFlow, you have some tokens here and the weights. This is our model of a repository. You can do exciting things on top of this model. Well, the first and the most obvious one is you can do topic modeling on top of this weighted bag of words model. This is what we did. Last year we had a post on Hubber about it. And we actually wrote a paper, me and Isa. Say hey, Isa. Hey. Yeah, thank you. And this is an example of our topics. It's topic number 36. I'm just literally writing it 36 because it's open. We are open sourcing everything, and we are opening our models, so you can be able to download it. You apply it to your projects if you want. Yeah, so it turns out that this, movie review, season, director, everything here appears as identifiers in source code, and different projects tend to use them in the same, in the same bag, and you can infer this, a kind of conceptual information about movies. So it has a season, has a DVD, so on and so forth. Our model had 320 topics or so, and some of those topics were really funny, like repositories related to food, repositories related to Portuguese, Spanish language. Yeah, it's really diverse. But I'm not going to continue with that because I'm still diverging. What we do instead, what we focus on is on identifier embeddings, as I mentioned. If you look at the repository as just a stream of these splitted and stamped identifiers without, counting frequencies, it looks the same as a sentence, more or less. And if you say that, okay, every file is a sentence, you just apply word to vec and get something. Yeah, that's what I basically said. The only problem is that if you have 16 million GitHub repositories, your dataset size is going to be 70 terabytes in compressed format, and if you uncompress it, it's going to be like 1 petabyte. And if you apply fast text or any other word-to-vec engine to these giant datasets, you are going to wait a long time. So instead of scaling with the dataset size, we are going to scale with the vocabulary size. The same idea as you had in Glove. You may have heard about Glove, right? But it turns out that there is a better model, which is called Swivel, developed in Google. So yeah, it also works on the co-occurrence matrix, sorts by frequency, reshards, and pass every shard of co-occurrence matrix to a separate node. It scales really well in a cluster, it scales really well on GPU. This is why we love it and use it everywhere. We forked it. We had to, because we had to, that's our stuff, it's open. And we have ongoing efforts to generate this co-occurrence matrix on Spark, because initial code, it has only native implementation on C++ working on a single node. And if you have 1 petabyte of information, even if you have a really good, fat, I don't know, 64 core node, it's still going to take a lot of time. So Spark is the only way for us. So it kind of works. You can try it, but expect some bugs because it's so better quality. This is how Swivel converges. You have a degrad inside. This is why at first it's going to, kind of try to explode, but a degrad actually works. It adapts to the learning rate, and after this small peak, you start learning well, and finally converge to something like loss 80. Yeah. It's not obvious if how 80 compares to the initial 260, but from my experience, if you have 3 or 4x convergence, it means it learned something useful and works well. We set embedding size to 300 and the window size to 20, if I'm not mistaken. This is the resources which we used to run our pipeline for identifier embeddings and how much size on disk it used. So actually, we didn't use all the GitHub repositories yet. It's ongoing effort. We just took 140,000 most top starred ones. Well, stars is not a good metric for estimating the popularity, but still, at least it correlates. So we don't have anything better at the moment. So this is why we use stars. What we shouldn't, of course. It took us about 3 days to clone all the repositories, and we got about 2.6 terabytes on disk. Then we applied this, parsing, classification, splitting, stemming. Took us about 4 days, and we reduced it to 2 terabytes. And then fast prep is an utility from Swivel, which runs on a single node. We optimized it, to work better, but still it took 2 days, and you end up with 20 gigabytes sharded coherence matrix. Finally, you apply TensorFlow with Swivel and get about 5.6 gigabyte embeddings file. So let me show you the results. I'm not going to, click this link and wait until t-SNE converges and everything. So this is a final result. This is top 10K word to vec from Swivel. And let me pick some nice example. At least I'll try to pick some nice example. I think it's something from OpenGL. Yeah, so this is how we catch Objective-C API, for example, NS prefix create. Looks very abstract. Okay, so this is how it looks. If you run it on a single repository, it usually catches more meaningful information. For example, on Linux kernel, it nicely groups module by module. Here we have, more vague, more abstract relationship, but still statistically significant. All right. So after we get these identifiers, we need to develop an algorithm to find nearest neighbors. It turns out that word movers distance works best and gives the best results from what we've seen so far. It's not the fastest algorithm, but it works. So what you do is that you solve a linear programming problem. So you map different words to each other. Words have weights, and you have a cost for transitioning one word from the other word. And it allows you to take into account synonyms. And word2vec gives you exactly that. It allows you to group synonyms together. The only problem is that a word mover's distance, as all the rest linear programming problems, they scale as cubic to the size of a sentence. It's good if you have a typical natural sentence like 20 or 30 words, but in our case, you have hundreds of words inside the repository, and yeah, it is going to be slower. This is why the original paper, it had a number of optimizations to eliminate as much evaluations of word moves distance as possible. They have a 3-stage pipeline. At first they sort all bags by centroid distance. Centroid distance is just, you sum all the words and divide by their number. This is called a centroid. Then you evaluate first number of VMDs, well, corresponding to the number of neighbors you need to find. And then you use the second relaxation as an upper bound of your distance. So a nice thing about WMD is that it has a relaxation which is always greater than the actual distance. So if the farthest nearest neighbor so far is smaller than your solution of the relaxed problem, you can just skip this sample and say, okay, it's not going to be inside. And this is mathematically correct. It allows you to skip about 95% of all WMD evaluations, which is good, but still not enough if you have millions of samples, I guess. So the bottleneck is still WMD evaluation. Since we work with Python, we had not so many, choices what to use. Usually it's PyEMD, and there is a second project called also PyEMD. Not that good. And I think the code which they use is actually the same, but the authors do not know each other. This is weird. So it takes about 2 seconds on like an average bag of 500 words, and it's not satisfying at all. We had to write our own implementation. We kind of a bit improved the second relaxation, and we used linear solver from Google to solve the actual min cost flow problem. And now we have only 0.1 second on the same bag, which is 2 times faster. Our average bag size is about 360, so from 500-600 it starts to grow, cubically, and in this region it's not that, long, so it works more or less okay for us. So let me show you some examples. This is our, working notebook. It's not fancy, but it allows you to evaluate all nearest repositories to the one you specify. So which one you want to get nearest repositories? You say it, I evaluate it.
Rust.
Rust? Is it Rust?
I guess it's Mozilla Rust. I don't know.
Let's try.
It's rust-9/rust. -9.
Oops. 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 Okay, so it is in our dataset, which is good. So the first step with word centroid distances was the fastest. It's only 1 fraction of a second. Then, as I said, you evaluate first k distances, which is 3 seconds. And now you do this tricky thing with second relaxation and skipping repositories. So from my experience, it usually takes from 2 or 3 minutes. Let's return to this after I present some, already calculated examples. This is what we get for Torch. This is actually very exciting because big DL project, it's not Torch, it is inspired by Torch. So it mimics API, but it's written in Java, and it's not that much just stupidly repeating all the stuff from Torch. But we still were able to find it, and this is really good. Of course, we found some models from Torch, different models, FluidNet from Google, and we found PyTorch. Second example, so this is Java, this is Python, but still API is very related to each other. This is our library which we use to clone GitHub repositories written in Go. It's very efficient. We had to write it because the rest of our pipeline is also Go, and it's good to have everything in a single language. It's also good because we found different Git libraries. This is like a competing one, which uses libgit2 as a backend. Our library is a complete rewrite, complete implementation from scratch. Gandalf. I don't even remember what is Gandalf, but yeah, I believe all of them are related to Git and working with Git. So I think it's a target. ppenf is an alternative to virtualenv, I believe. And you get other alternatives here, even py2dep or pipc, whatever does it mean. For Spark, you have projects related to Spark, and actually you even get Hive. You have Solar. For MySQL, it's pretty straightforward because MariaDB is a fork of MySQL. You have all sorts of projects from Percona because Percona is also working with MySQL. You have AliSQL, which is basically a fork of MySQL written by Alibaba. For the language compiler, you get other languages. You have NIM, you have smaller C, and you have GDC. It's D-lang compiler implementation from GCC. I think these are like other pet small languages. It's very interesting that it grouped the project this way. When we showed these results to our team, one of the engineers, his name is Honho, was really excited because he likes NIM and D a lot, and he was like very happy that we group them together. For WordPress, you get all sorts of websites using WordPress, and you get Angular WordPress, which is WordPress for AngularJS. For Homebrew, you have Chef, which is very interesting because it was able to understand that Chef is related to Homebrew, written in Ruby, I guess, sharing the same patterns inside. Yeah, Tiger Brew is a fork of Homebrew, even Brew2Dep. At the same time, it's not always working that exciting. If you take Coma.ai OpenPilot, it's a self-driving car implementation from Coma.ai startup. It's a very unique project. You don't have other OpenPilots on GitHub available. So the output from here is not, very relevant. I can only say that probably Deep Belief SDK is a bit relevant because OpenPilot has deep neural networks inside, and well, it's only just single, probably sensible result. Finally, since we are working on a weighted bag of words model, we are not, forced to use a repository as a query. You can use just any artificial bag of words you can create. So, for example, if you write something like, write in Google like beer, ale, APA, like lager, all sorts of beer-related stuff, seeds, barley, you get the output of all GitHub repositories related to beer. You have Open Beer database, you have Good Brew WS, you have Beer Swipe Refresh, which is progress bar for iOS mimicking a beer glass, very funny. You have Raspberry Pins, which helps you to brew beer on Raspberry Pi. So yeah, I believe it can be useful, at least for people who brew beer. Let's check if you have any results. All right, so it took 1 minute. And this is the result.
Can we open some?
So it's Rust syntax backport. So I believe it's a backport of some new features to the old core of Rust. I'm not familiar with Rust, this is my guess. You say if I'm right or wrong.
You better talk to the microphone. Yeah.
Let's check another example. Miri. Experimental interpreter for Rust mid-level intermediate representation. So it's also a project focusing pretty much on the Rust language itself. And well, I can look at other examples, but I think this is also some attempt to put Rust on a web browser. Yeah, I think this is syntax. Looking at scene, probably it's also focusing on Rust and some syntax features. So it makes sense to me. It looks relevant. Probably it's not that good as a completely handcrafted list of related repositories, but I think it's rather well created. Oh. About the future. We are going to open source everything. Some of the stuff, for example, datasets are already open on Data World. We are open sourcing the API, the model systems, the pipelines which we use to create the models. So everything should be replicatable. And if you don't want to replicate it and just use a ready model, you can use the model. And we are going to improve our identifier extraction pipeline by leveraging Babelfish. The thing is, when you do identifier embeddings, as you saw, we just put identifiers in the same sequence they appear in the original file, but it's not always a good idea because some identifiers should appear near each other. Even in the file, they're not very near each other. For example, you have a giant for loop, and after the giant for loop, you have some other code, the identifiers from the bottom part should be near to the identifiers from the top part, and even to identifiers in the for loop. So we believe that using trees instead of this dump regular base expression patterns should improve the quality of for2egg. As you may notice, it took 1 minute to find a repository similar to Rust. Probably it's more or less okay, because at the beginning we had 1 hour, so 1 minute is much better than 1 hour. But you cannot use it for online services. You cannot scale it to many people, many users. Probably we should don't be that much precise, sacrifice some quality, and just use something else. For example, there is an idea to apply survival for the second time, because you can look at the repositories as sentences themselves and embed them as context, because survival has an abstractions for context and for words. So you supply word embeddings from our first trained model, set them as read-only, and embed only the contexts, and you get the same vectors for repositories. And if you turn every repository into a 300-dimensional dense vector, it's very easy to just apply key nearest neighbors, and that's it. Facebook has just recently released Phase. It's a really exciting project which allows you to find nearest neighbors on GPU cards. It works super fast, like fractions of second for billions of samples. So probably we should use it. Oh, I forgot my clicker. That's it. This is my contacts. Thank you. Questions? Doubts?
Hi. I have a question. How sensitive is the method to the language of a project? Like we saw with the Rust example that many of the projects were related to Rust, and probably they were also written in Rust. Like the Rust itself is probably written in Rust. So, for example, if you ask for Django, would some similar web framework for Ruby appear similar or not?
Well, initially we do not distinguish language from the language. We have a universal model, and the answer is it depends. For some projects which have very recurring specific pattern for a specific language, you are going to end up with projects written in the same language or framework. For example, WordPress. But if you look at, for example, GoGit. Oh no, this is a good example, decompiler. You have NIM language here, and NIM language and D language, they are very different, written in different languages, yet still they are grouped together.
Hi, could you please explain how do you apply your techniques in real work? What kind of applications this analysis have in your company, maybe?
Well, initially we wanted to create a product where every developer can log in and get recommendations, people he should work with, repositories he should contribute to. But later we switched to more engineering stuff, like supplying the underlying models, providing the platform, and letting other people decide on what to do with these models, because apparently you can do a lot, but we just, we supply the infrastructure and platform.
Thank you.
Do I correctly understand that Swivel is a kind of glove embeddings, I mean word embeddings?
Yep.
And do you have any plans to use recurrent embeddings for source code?
Sorry, which embeddings?
Recurrent, kind of RNN embeddings, kind of paragraph to vec or doc to vec, some kind of this thing.
All right, thank you. So yeah, Swivel is a kind of an improved glove. It scales better with all these shards and everything. The loss function is a bit different. Well, probably the paper is biased because the authors of the paper, compare it with glove and say, okay, it's much better. But they are the authors. I don't know about other papers who compare glove and Swivel, but we believe, it's better. As for recurrent embeddings, the problem is that applying a recurrent neural network to, terabytes of input, it usually works really slow. So in our case, we still have linear complexity because we have to convert our dataset to a concurrence matrix, but we can do it very efficiently on Spark and so on and so forth, on many nodes. Recurrent neural networks, it's a single brain, and you cannot scale it to different nodes, train them independently on each other on parts of the dataset. So for this particular application, I think it will be too slow, unfortunately.
Hello. So you have this bag-of-words model over all identifiers in the repository, right? So I imagine that each individual repository contains like millions of unique identifiers. So why it turns out that the average bag size is just 360?
Okay, it's a good question. So let me click to the pipeline. So first of all, we throw away identifiers which are less than 3 chars. It's quite a few. Then we filter identifiers which occur only once. Not only one, I think our threshold is 5 occurrences. So if an identifier is very rare, like less than 5 occurrences throughout all the GitHub, we don't use it. And usually this is the majority. So what we've got left is only a small part, which is like 500 or 1,000 for very large projects at most.
Okay, thank you.
Hi. Have you thought about whether it would be useful to have different similarity metrics for different end applications? And if so, how would you go about doing that?
It's a very interesting question. We didn't think about it. What applications do you mean exactly?
The user might have different information needs. So, for example, whether you're looking at tools for processing Rust code versus different implementations of Rust.
All right, thank you. So I think there is a possibility to combine this recommendation with our topic model. It's over here. Yep. So it should allow you to pick from a predefined list of 320 topics or so to narrow down your search. You should narrow down by specific ecosystem or technology, language. I'm not sure if we can do better than this. Yeah, probably we should think about it. Thank you.
Thank you for good presentation. I have a question about, I noticed that you are making almost end-to-end machine learning, but you have one step pre-processing that is some kind of rules that you applied to split some names into subnames and so on. Did you think about applying some end-to-end deep learning algorithm like character n-grams and then combine them together to provide embedding for this word?
Yeah, thank you. That would be very funny to try actually, because in our identifier splitting algorithm, I just used expert knowledge from my experience as a programmer. This is what I see, how people can name identifiers. Of course, it's not fancy. You should be able to infer this using a neural network, and RNN, for example. Yeah. Or, well, the thing is, we are using like unigrams here, basically, right? We could try to use n-grams instead of that. So it's an unexplored area. Yeah, it's a good suggestion. Thank you. Thank you.